Computer chips have revolutionized our lives over the past half-century, and they're getting ever more powerful and essential. Can you imagine your life without any of these devices? At least I can. Part of the key to this success is the technological advancement that has been achieved in semiconductor industry. We have managed to double the density of transistors packed on a chip every 2 years. That's why we're no longer using these giant machines, but these much faster and smaller devices. It is widely believed, however, the conventional technology that's built on silicon electronics are fast approaching its physical limit for further shrinking down. Therefore, alternative technologies are in hot pursuit to replace or complement the current silicon electronic chips. Among the many alternative technologies, optical devices are believed to be a promising candidate. Hi, I'm Lin Sun. I'm a PhD student at Material Science Department in Northwestern University. My research focuses on building optical devices with DNA-assembled nanoparticle superlattices. Unlike electronic devices where electrons are the information carrier, small packets of light or photons are the information carrier for optical devices. So they are believed to drastically increase the device efficiency because nothing travels faster than light. However, with its unique properties comes its unique challenges. Unlike electrons, which flows in a closed circuit when a voltage is applied, it is very hard to manipulate light. Therefore, an optical circuit will require many different components to work together in order to produce, transmit, and receive information in the form of light. In order to address these challenges, it is very crucial to find materials that interact strongly with light and fabrication methods that allow us to precisely control the structure we make down to nanometer length scale, a length scale so small that we can't see with our naked eyes even after it's been enlarged 100 times. This is where my research comes in, with the help of a special friend, DNA. We all know DNA is the basis of life. Its genetic code programs every single cell in all living organisms. The genetic code can also be used to program material design. By carefully designing the DNA sequence, we can program it to selectively bind to target DNA with complementary strands. Now, if we attach a particle similar in size as the DNA, so nanoparticle size, as I talked about, the DNA can act as bond and the particle as atom, just like natural materials. Except that we now have created a new class of materials, and what's important and interesting for this new class of materials is that, first, we can pick the particles to be able to interact with light strongly. As a result, researchers have shown that these particles have demonstrated new properties that are not found in nature, and they can lead to more interesting applications, such as invisible cloak. Moreover, we have precise control on the structure of the materials by simply programming the DNA to be longer or shorter. And if you remember from the beginning of the video, these materials that interact strongly with light and the fabrication methods that allow precise structural control are exactly what's needed to solve the biggest challenge in making optical circuits. So one day, your computer or phone chips might be built on DNA, and they run much faster with the size of your fingertip.